Okay, 5.2 is our first technique other than the basic rules. Integration by substitution. Before we learn the technique, let's go through a couple of problems we're going to verify. Verify the given solutions. To the following problems, which are going to be antiderivative problems, but they're going to be more complicated than we're used to seeing. But you'll be given the answer. And you just have to verify the answer. So that's an integral which looks really ugly. The way you would do it before in 5.1 is probably expand that to the fourth power. Or it's going to get massively distributed to 10x, get a bunch of terms, probably like 6 terms or something, and then do the power rule on it, and then get an antiderivative with that many terms. But we're going to also learn to just leave it in that form and deal with it in that form and get a somewhat cleaner version of the antiderivative, the equivalent answer to what you would get if you expanded it and did the power rule. But here we're going to learn how to go straight from there to there, not having to expand a fourth power of that x squared plus 3. But we're holding off on that because now I just want to verify the solution. Okay. All right. So the way we verify it, it's an antiderivative problem. To check it, this is basically verifying it is doing the check that we talked about that I did one time because I said you don't have to if you're convinced your answer is correct. I'm pretty convinced my answer is correct, but we'll check it anyway. And we want to see what happens as we take the derivative of that. I mean, I could throw in the plus c, but that's going to be a constant anyway, so let me actually throw it in. Okay. So we're going to verify that's the antiderivative of this, which means that when we take the derivative of it, wait, what did I just say? That's the antiderivative of this, which means when we take the derivative of it, you should get back the integrand. Okay, that's in the warning for me. I'm a little bit shaky. Okay, we're going to do the power. We're going to chain rule on it. So the 5 is going to come down, and this x squared plus 3 will be to the fourth power. But then I have to do the chain rule on the x squared, which means, or sorry, the x squared plus 3 technically, which means that I'm going to get 2x via the chain rule, and then the plus c is just, the c is a constant, so the derivative of that is 0, so that gets eliminated anyway. I wouldn't even have to include it if you understand that. Okay, anyway, let me clean it up. Notice how I get 10x because the 5 came down from the power when I did the power rule. And then the chain rule on the x squared gave me a 2x, which gave me a 10x that's there. And then I have x squared plus 3 to the fourth power. So even though right now this is pretty obscure how you can go from that to that, what I want you to note is how the chain rule, the power comes out here, the 5, and then via the chain rule that 2x ends up combining to give me that 10x. So what that means is, you have to write this down, but if I gave you something like this, it'd be pretty hard to do without expanding it out. That's actually really difficult. But giving you this problem, which at first seems like it's more complicated than what's above, this is actually easier to work with, or it will be easier to work with once you learn the technique, because that 10x there, or specifically that x there, makes it work out nicely because of the chain rule. So what we're going to be doing in this section is basically learning how to reverse the chain rule. How to be able to see that this, the 10x, or sorry, the 5x from there, sorry, the 5 and the 2x are all coming out of the chain rule with that power and the chain rule on the x squared. But we have to organize it where we can go backwards. Hence, the technique that we're learning, integration by substitution, is sometimes called the reverse chain rule. I'm going to do one more of the same thing, verifying the given solution. I didn't leave myself room, but I'll cram it over here. Okay, let's see. So again, it's going to look unnecessarily complicated. It has 21x squared e to the x cubed dx. And again, it looks like a very difficult antiderivative to do, but it's actually not going to be. It's going to be fairly straightforward once we understand what we're, no, sorry, not no, once we understand how we're going to reverse the chain rule. So the antiderivative is going to be 7e to the x cubed. That's it, a fairly clean antiderivative, because, and anticipating what I'm going to be doing here of verifying, when I start doing I'm going to take the derivative of this, the c is not going to matter, I'm going to be doing the chain rule on it, so it'll be e, that'll stay alone, as is, x cubed, and when I do the chain rule on the x cubed, I'll get a 3x squared, which will multiply by that 7, which will give me that piece there, the 21x squared. So that 21x squared actually makes it work out nicely. Hard to see in advance, but let's actually work out what I just said. Don't worry, I wasn't going to just go verbally. Plus c, but I'm not going to bother because it's going to go to 0 anyway. All right, so we bring the 7 down. That's going to be part of that 21. I'm going to do the derivative of e to the whatever is e to the whatever. But the chain rule on it says I have to work on that x cubed. The derivative of x cubed is 3x squared. So I'm getting a 3x squared via the chain rule. Multiplied by that 7 gives me that 21x squared. So the 3x squared that's in there is coming from the chain rule. And so that is the antiderivative of that, because the derivative of this will give me back the integrand. Okay. So let's learn how to not do it without me giving you the answer prior. Let me see, I'm gonna do that one first. So, well, I gotta write some steps first, or some general overview of the technique, integration by substitution. I mean, that's the title of the section, but you're gonna use a change of variables to, and I'll put in quotes because it's not a formal term, but reverse the chain rule. And so this is something that's called the reverse chain rule, informally. And what we're going to do is let a variable u equal to some function of x. Now they in the book call it u of x, so it's going to be confusing. We're going to let the variable u be an expression involving x. We will need to then find a derivative of u. You'll see in a little bit, this is me just summarizing what how the book outlines it, but it's not going to make sense until we work through an example. You're going to be taking the derivative of this, which will be the u prime, and we'll use a d notation for the derivative of that variable, which means that the dx we're going to be converting to du, so you'll get a du in that. And again, I'll emphasize it in a bit, but we will have to do this step is finding du. Alright, and another thing I want to note, first of all, because technically you can use any letter you want, but the standard convention is to use u in this situation. We're going to be substituting x, replacing x, the integral involving x with an integral involving u typically. You can in theory use any variables. They want to avoid using y and x because they'll reserve that for the y. Sorry, they want to avoid using y and z as substitutes because they'll be using that in multivariable calculus. They'll have x, y, and z, and the 3 coordinates for a 3-dimensional surface. But so they want a different letter from x, y, and z. Use a standard. Sometimes if they have to do 2 steps, they'll use a w, or you can in theory use anything. But u is common, and hence this is often called u substitution. An important thing is it often involves trial and error. So you're going to be setting u to be some expression involving x that you see there. It may not work, and you just go back to the drawing board. You start working this out, and if it's not working out the way you want it to, you just go back and reset u. So this is your option on setting u, and sometimes you don't know what to do. But the thing is to just start trying things if you know it's going to be u substitution. So let's work on our first example. Here it's just find the indicated integral. You can assume that we're going to be using substitution. But in the future, when you have many, many integration techniques, all of the whole arsenal of them, you will often have to just look at an integral and figure out what you're going to do. And substitution may be one of the options that you might try, but you might have to try trig substitution, partial fraction, integration by parts, a bunch of things that comes up in the next semester, not here. This is the most basic technique, so this comes first in your lessons on how to handle weird-looking integrals. Okay, so I'm going to work this one cleanly and just show you how it works. I'm not going to do the trial and error and do fake things that aren't going to work out. I'll do that later. I want to talk about, like, you just got to try things, see that it doesn't work out, and go back to the drawing board. Here I'm just going to do a smooth one where it works out nicely. Basically, you have at your disposal, well, you have in your integrand e to the x cubed. You don't have an antiderivative for that, and you definitely don't have one for that has x squares involved. And the only thing involving u that you know is, oops, the antiderivative of e to the x, which is just e to the x. That's the only exponential antiderivative that you know, and therefore to do this, and having only substitution available, you needed to basically have a single variable there. Meaning you can't have this x cubed there. You need just a single variable. I want to rewrite this as u, because that's what we're going to be ultimately doing. But so anyway, the antiderivative of e to the u du, that's just the same integral but with respect to u, will be e to the u plus c. So because that's the only thing we have, I basically, my hint, or I kind of suspect that what I'm going to be doing is setting u to be, and you don't need to write let u equals every time. I'm going to let u be equal to that exponent for the exponential, x cubed. And don't worry about anything else. That's our setup, and that means that piece right there is going to be e to the u. You got a lot of other stuff going on. You got the dx first of all that needs to be converted to a du, and you got that x squared, which looks like it's making it more complicated, but it is actually going to make it work out nicely. So what we need to do now is do this step where we find du, an expression for du. So what we do is the derivative of u is just going to be du. That's the notation. Can't really get into too much detail about what it means, but anyway, that's what we're going to do. Then on the right side, you're going to actually take the derivative of this with respect to x. It's going to be 3x squared, and you're going to write in a little dx every time you do that. It's sort of like the implicit differentiation where it's like that's your dy dx part of it, the dx. Again, we're not getting too much into it, but anyway, that's what you're going to do. When you take the derivative of this, you're going to have a du on the left, and you're going to have an expression with dx on the right. Okay, and so now you're going to rewrite this integral in terms of u. You're going to rewrite an integral with respect to x in terms of our new variable that we introduced, u. Alright, you've got to look at the pieces. So first of all, I have e to the x cubed. That's going to be e to the u. I'm going to start writing it up, but I'll clean it up afterwards. So that piece right there is going to be e to the u. My dx is right here, and I'm going to convert that to a du. So basically every piece needs to be converted to u. I have a dx there. That's what I'm going to be using to substitute dx in terms of du. But I have this extra x squared there in this expression, which is kind of perfect because I have this x squared there. So let me rearrange it. You won't necessarily be rearranging every time. God damn it. But I'm going to start breaking it apart in anticipation of how I'm going to get everything to be used. First of all, I'm going to split off the 7. And leaving what's left inside the integral, I'm going to have e to the x cubed. I'm going to combine the 3x squared over here with the dx. And I just want you to pause and note that this is equivalent to what's above. I'm going to organize it a little bit better next time, so you don't have to. You're not going to have to creatively split it up to get exactly this. We'll have a better system. But for now, I just want you to see that the 7 is going to be a 7 regardless. There's no 7 that I can count for there. But I split off a 3x squared, combine it with the dx literally because I see that right there. So that accounts for that, and then I obviously have the e to the x cubed. So if you multiply all this together, you get back the original. So it's just me rewriting in a different form, so you can see what's being substituted. Okay, then the 7 is going to stay. The e to the x cubed is going to be rewritten in terms of u. U is equal to x cubed, so that's going to be a nice clean e to the u. This whole 3x squared dx is right here is equal to du. So you need to rewrite your dx in terms of du. You need to have an integral that's just in u. And the main thing that trial and error is going to come into play is you need to have an integral that you can actually do. So sometimes you do a u and it works out nicely, but you end up with an integral that you still cannot just do instantly or without major work. So the idea is to get an integral that's a little complicated and make it into a simpler integral that you can do using the rules that you have. And we can definitely do that. I'm just trying to figure out where I'm going to go. I'm going to go over here. I'm going to go over here, sorry. And so I'm going to take the antiderivative of that. It is 7e to the u plus c. We're not done. Our answer can't have u because there was no u in the original problem. We introduced u ourselves. So for our final answer, we need to take it back to x. But I'm just going to use that substitution. U is equal to x cubed. And that should be my antiderivative right there. Going back to x. I can check it. I did it earlier, but let's check it again. Let's see how it all worked out. To check it again, I'm just going to take the derivative of that supposed antiderivative. I'm going to drop the plus c because it's going to be 0 anyway. And let me see. I'm going to get 7 chain rule on the e to the x cubed times 3x squared. And I'll get 21x squared e to the x cubed. And that checks out. Yep. That's how we're going to do it. And this whole section, mainly examples. There's a few applications in the homework and the exercises in the back, but I'm going to hold off on applications until the later sections of chapter 5. This section, I just want you to grind out some practice in doing this technique. And we're going to do several examples showing you the different things that come up. I'm going to pause it. Okay, so same instructions. We're just evaluating find indicated integral. This is going to be a little more basic. Still going to be exponential. We'll get to other ones later. Okay, let's see. U is equal to, again, this one's pretty straightforward because you literally can't do anything other than e to the u, or a single variable there. So you definitely probably want to make u equal to that entire exponent. This one's not going to come out as cleanly, but this is more how you're going to approach it. All right, I need to do the du immediately. As soon as I said u, du. My du is just going to be 8, just 8, and then I got to put a dx there so I can relate dx to du. All right, and what I didn't do this last time, but what oftentimes is you can just isolate the dx, meaning I'll divide both sides by 8, and I'll get dx is equal to 1/8 du. All right, and then rewriting my integral. Okay, e to the my entire exponent is u. I set it to be u. My dx right here, dx is equal to 1/8 du. All right, the 1/8 constant I'm going to pull out, and then I got an integral that I can do, e to the u du. The antiderivative of e to the u is e to the u times 1/8 plus your constant of integration. That's sort of our answer, other than you want your answer to be in terms of x. U is equal to 8x plus 3, sorry, 8x minus 3. So we just substitute back in 8x minus 3. And that's it. You can check it if you want. That'll definitely work out. So as long as you're confident that you did your work correctly, that'll be your answer. The derivative will be e to that whatever, and then the chain rule on that will have an 8, which will cancel that 1/8 and give you a clean coefficient of 1. So that's how that's going to work. Let's just move on. So we're just going to grind a bunch of these. Let's see. Let me go to the first one. Yeah. I have others, but yeah, let me just go back and make sure you can understand how I got that answer for that first integral that I did. Okay. or the integral that I give you the answer, and we verify the solution. Okay, you could expand it out and actually work with it, but a shortcut, so this has many options, but I do have this base to the 4th power, and I can set u to be that base. Because I can't really do the x squared plus 3 to the 4th and antiderivative of that as is, but I will be able to do it if I can get a u to the 4th, and then it's just the power rule on that u. So that's why I'm going to make that entire base to the 4th power u, so u to the 4th. I have extra stuff there, so let me account for that, or see if it's going to work out. It may not work out, because I have that extra x there. The 10's not a big deal. I can pull that out and just not worry about that for now, but I do have an extra x, and that's going to be an issue, or it would be an issue, except that when I do my du, which again is in that very next step, I'm going to get 2x, and then I always put a dx there. So that means that extra x there in my integrand is perfect, because I will have that extra x there. I'm gonna, technically I could split off a 2x and then pull out a 5 and break it up that way, but I'm gonna pretend like I don't anticipate that, because it's not gonna be as nice numbers in the future. I'm gonna do what I did over here. Let me just get my x dx alone. Any constants I'll move to the other side. So I'll have x dx is equal to 1/2 du. So I'm going to pull out a 10. I'm going to go back to the original. I'm not going to put u yet. I'm going to, and people don't write this stuff. They just, once you figure out how everything is accounted for, you can just go to rewriting things in terms of u. But let me take a moment and actually just rearrange things a little bit at least. So that's what I have. The 10 I pulled out. The x squared plus 3 to the 4th is my main chunk that I'm working with. I have that extra x, which I'm going to move next to the dx, and note that that becomes 1/2 du. So the 10 stays 10. This x squared plus 3 to the 4th becomes u to the 4th. And then this whole x dx, the x together with it, worked out nicely to just a 1/2 du. So that extra x was perfect. It actually makes it work out nicely. Okay. And then now I'll move things around. Well, I'm going to put the 1/2 constant. That's going to give me a 5 out there when I do 10 times 1/2. And so now I just have a basic power rule. So I'm going to do the power rule on that u to the 4th. I'm going to raise the 5th power over 5 times that 5, and then plus c. Okay, the 5's are going to cancel, so I get a clean u to the 5th plus c is my antiderivative of this integral, but I want the antiderivative of the original, which means I have to just rewrite it in terms of x. U to the 5th is going to be x squared plus 3 to the 5th dx. Okay, so that x, which makes it look like it's making it more complicated, actually makes it nicer, because when you do your du, you get that x dx. I do want to note that as a side thing. That's not going to work. That's my answer, by the way. What did I just write? Plus c. Again, it's early morning. Okay. I'm going to mention something that's not, it's not a natural problem we're going to work through, because basically it's not going to work out nicely. If I had that, which again makes it initially looks like it's easier than that, it's actually not easier. In fact, I'm not going to be able to do this. Because if I tried to do exactly what I did there, I have this extra x that came up, which was perfect on that last one, but it's not so perfect here, because I'm not going to be able to rewrite this in terms of u. Sometimes people will write, that'll be u to the 4th. So sometimes they divide it by x, so you have that. But what that means is you're going to have still x's in your integral. You can't convert half of it to u's and leave some x's there. You're not going to be able to do it. X is a variable. So this means, it didn't work out and I don't know what to do. So substitution did not work there. What I would have to do is expand it out. I would have to multiply out for the 4th power and just do polynomial antiderivative. So this one was way worse than that one. That x made it work out conveniently. And these were designed to come out nicely. they're designed to work via substitution, which means it's basically a puzzle that they're expecting to solve, and that puzzle worked out perfectly, but that one was not one that I could give you in this section because it does not work via substitution. Alright, so substitution doesn't work with everything. They have to work with problems that are designed specifically to work out. Alright, I'm going to do this one. It's a very similar problem. I think I based it on that. I don't remember writing it, but apparently I wanted to use the same factors, just a different power. Alright, let's see what we got. Sometimes people will write, well, you got to set u to be some piece that you see here. U is equal to x. If you see that x there, I've seen people do this and they work it out, and basically u is equal to x will never work out to anything, because all it's going to do is your du is equal to dx, and basically you get the exact same integral. Nothing simplifies. It's going to be the exact same integral, but in terms of u. So doing u is equal to x just rewrites your whole antiderivative exactly the same, but with a different letter. So that's definitely not going to be a thing that's going to help you. The only other piece that I see here that makes sense, and again, these are pretty simple to start off with, is that x squared plus 3. So I'll have that in my denominator to the 7th power. That's pretty simple to work with. I do have that extra x. And a lot of times when you see people working these out very quickly, and it seems like they just know what to do, it's not that they know what to do, it's that mentally they're going through anticipating what you're going to get when you do your du. So I can kind of tell it's going to work already because I do have that extra x, but I'm anticipating when I do my du, I'm going to get that extra x accounted for. So whenever it's a polynomial, your du is obviously going to have one less power than that. So it'll have 2x dx. Perfect. That x works out perfectly with that. Alright, I'm going to do what I did before, which is just isolate the x's only. Constants I'm going to move over. Easier to work with. And I'm ready to go. I'm not going to necessarily split it up that way or rearrange things so you can see what's happening, because people generally don't do that as they get good at this. But you're noting that that x and that dx combined becomes a 1/2 du. And what's left is 1 over, and that's going to be my base, which is u to the 7th. And that's what I got. So I could rearrange it. I could put that x next to the dx like I did last time to make it seem clearer to somebody watching me do this. But as you work this, they're just going to expect you to know that that's combining with that to give me my 1/2 du. That's going to give me u to the 7th on the bottom, and I'm ready to go. How do I handle u to the 7th on the bottom? I rewrite it as u to the -7 and do the power rule on it. Add 1, divide by that power, bring this half down, tuck on your plus c, and so I'm going to get -1/12 u to the -6 plus c when I clean it up. And then again, I got to substitute back in terms of x, so I'm going to get the x squared plus 3 in there. And that's fine, but if you want, you could also move everything to the bottom. X squared plus 3 to the -6 power is like x squared plus 3 to the 6 on in the denominator next to the 12. So either one of these is good. Okay, let's see. $15x squared minus 5x plus 10 up top over the square root of 4x cubed minus 2x squared plus 8x minus 5 dx. That's my antiderivative that you're expected to do. Looks super messy, but since it's in the section 5.2, integration by substitution, it means substitution should work. But let's see. So you get a bunch of polynomials. And sometimes, again, setting u is a trial and error situation. Let's see, if I set u to be that numerator, my d will then be 30x minus 5 dx. And now you're looking to see, is that going to help us? I'll have that numerator become u. My denominator, I have no way to express the denominator in terms of u because I got nothing that looks like it here. And my dx is going to have, I still have this extra x in my dx and I don't have that there. This is not working out. So abandon, it just was not the right choice in your u. Your other choice is to set u to be that expression on the bottom. Should you include that square root? You could, but then your d is going to have to be a chain rule on it, and it's going to get messy. I'd have to treat that square root as a negative half power. And this is all just substituting in terms of dx. That's going to make it more complicated than I think I need to. I think I want to try u to just be that radicand under the radical. And also anticipate what I talked about earlier, that if I set u to just be that, my d is going to have a x squared, an x, and a constant. It'll have a polynomial. My dx will involve a polynomial that's 1 degree less. And that's what I have on top. One degree less polynomial. X cubed, a cubic polynomial, and when I take the derivative of it, I'm going to get a quadratic polynomial. So that's looking like the best way to go. So I'll set u to be that radicand on the bottom, 4x cubed minus 2x squared plus 8x minus 5. I'm still not sure it's going to work, but it will because I designed this to work. But it's going to be a little bit messy. I'm going to take my derivative. du is equal to 12x squared minus 4x plus 8 dx. Whew, okay. And now what a lot of times is you'll be able to actually make that look like that, but one thing you want to do is maybe factor out a common factor. I don't want to divide x's and move x's with the du, but I can move any factors out. Not all of them, but I got to be able to factor out a common factor of 4. So this one I got to get creative and work with it. Kind of knowing that these problems are designed like a puzzle for me to solve. So I'm going to factor out that 4. And I'll divide by that 4. The simpler the expression with the x's, the better. So 12x squared minus 4x plus 8 was too much. I can't really do anything more. I'm not going to be able to move a 3 over because 3 is not a factor of any of these other terms. And that's what I got. Okay, let's start looking at what I need. My denominator is going to just be a clean u. I'll have the square root of u on the bottom because that's u is my radical on the bottom. My dx here, but it has this extra x, which needs to basically be equivalent to that polynomial on top, and obviously it's not. But one thing you can notice, a lot of times they will be multiples. Again, these are designed to work out. So if I multiply this by 5, I'll get 15x squared minus 5x plus 10, so it's perfect. I don't want to actually multiply by 5. I don't want to really mess with that. But I'll note that I'm going to rewrite my integral. So for now, I'm not substituting u yet. I'm going to rewrite this so it'll work out cleanly with what I have here in blue, all these du's or these u's. Okay, so that numerator, I'm going to factor out a 5. Oof. Now I'm going to get 3x squared minus x plus 2. Okay, factor out a 5 from that top. I could pull it out of the entire integral if I wanted to. I may do that later, but the main thing is to look and see if now this is working out, if I solve the puzzle. Alright, 4x cubed minus 2x squared plus 8x minus 5 in the square root in the denominator, that's my u right there. So I have a clean square root of u there, but I have a lot of other pieces that need to be accounted for. If I factor in that 5, I can see I got a 3x squared minus x plus 2, which is exactly what I have there. So that times dx together will be 1/4 du. All right, this is working out. So let me rewrite it over here. On the bottom, I said that whole radicand is going to be u, so on the bottom, I'm just going to have the square root of u. Up top, I have that 5 that I'm going to just leave right there. And as I mentioned, the rest of it, after I factor out that 5, 3x squared minus x plus 2 times that dx is equivalent to 1/4 du. And I want to let you know that sometimes they put the du, they can put du on top of a fractional expression, or they put it on the side. So when I pull that, I'm going to pull out that 5/4. And sometimes I'll write an integral like that. That's a valid integral. It does have the integrational, the symbol, and the du. They just didn't cap it off on the left and right like that. But that's some way. That's how they write it sometimes. I don't like to write it that way. I like to see my integram bounded by those two things. So I'm going to rewrite it this way. But it doesn't matter as long as you can interpret that as u and doing the antiderivative of u to the -1/2 because it's a square root on the bottom. All right, from there it's a fairly straightforward power rule. Ooh, not 3. -1/2 plus 1 is +1/2. I'm going to divide that by 1/2. Divide by that 1/2. I have this 5/4 out here I have to carry down, and I'll get a plus c as my constant of integration. And I'm almost good. I've just got to substitute back in terms of x. I'm going to flip that 1/2 over. It's going to become 10/4, which reduces to 5/2. This u to the 1/2 can be rooted into the square root. So it'll be square root of u, just rewriting it. But I'm going to go ahead and substitute my u. That's why I made it so big. My u was all that cubic polynomial. Plus e. And that's it. That is my antiderivative. It took a lot of work. One thing to note again is these are designed to work out nicely. They're already puzzled to be solved. So for instance, if I had a 6 instead of a 5 here, the whole thing doesn't work out and you can't do it. So again, this is designed where it fits perfectly. All right. Anyway, you'll see one like that on the homework. Where you have to factor out and get creative with your factoring. Like I had to, that top, I had to factor out a 5 first to see that 3x squared minus x plus 2. All right, I got more examples, but somebody's calling me, obviously. Okay, same instructions. As mentioned, we're just going to grind out a bunch of these. Solve a lot of polynomials, where we use a power rule. We did the exponentials in the beginning. Here, we're going to see some logarithms. And I do want to note that the antiderivative that pertains to what we're trying to do here is the antiderivative of 1/x is ln of the absolute value of x. The derivative of ln of x is equal to 1/x. You do not have an antiderivative for ln of x. That is not something you can do. It's not 1/x. That's a wrong way to go. This is a big question mark, and you can't do it until you get to the next semester. You have to do what's called integration by parts. That's not something we can do, but I don't want you to mistakenly think that that is equal to 1/x. The derivative of ln of x is 1/x. The antiderivative of ln of x is not a thing, at least not yet. But and we're doing antiderivatives. We're doing integration. And the only one we can do is 1/x. As far as clean ones, at least. This one is not so clean, but we will be able to get it away using substitution, obviously, because it's coming up in this section. All right, is that all I got? Yeah, okay. Again, on the homework, they might write it like this. So you'll see integrals like that. It's just that they put the dx in a numerator because there was nothing else in there. If I saw that, I would immediately want to rewrite it so I can see my integrand is 1/. x ln to the fourth of x dx. I do want to make sure we interpret that correctly. That's not x to the fourth in there. That's different from, that's entirely different for that fourth power to be applied to x. The fourth power there next to the ln function means if you're raising to the fourth power the ln of x function. So when I interpret it, and you don't have to rewrite it, but especially now when we're trying to incorporate this new substitution, we definitely want to interpret that correctly, and that ln fourth of x is ln of x, all of that to the fourth power. That's what we're looking at. That's what we got to deal with. Okay, let's see. Let me do some fake use that I know is not going to work out, but let me pretend we're doing trial and error. I have an extra x here. I mentioned that u is equal to x is not going to do anything other than changing every x to u, and you'll get the exact same integral, and it's not going to get you anywhere. It is an x in the bottom, though, so I could think of it like I do have a 1 over x in this expression if I interpret it that way. Maybe I can interpret that ln fourth on the bottom as ln of x to the negative 4. So I can think of it that way, and maybe I can get away with u is equal to that 1 over x piece. I'm not going to, but let's say this is my trial and error. All right, I got to do my du. Make sure you know the derivative is not ln, it's the other way, and so the the derivative of this is, I got to treat that as x to the negative 1. It's going to be negative 1 times x to the negative 2 dx. So du is equal to negative 1 over x squared dx. So that choice of u will account for that. My dx has an x squared on the bottom, and I don't have that. And I also got no way to account for this ln of x to the negative 4, so no, that's not working out. So this choice did not work out. Don't stress, we have many other options. So that's not even a good way to think about it. I do have this ln. I have ln to the fourth specifically, so now my question is, should I incorporate that? Should I do ln of x to the fourth the fourth power as part of my u? Then my du is going to have a 4 ln of x cubed and some other stuff with the chain rule, and that's probably not, it's not coming out cleanly the way I wanted to. That whole ln x to the fourth will be my u, but then I've got this extra ln cube, and I got too many ln's there. That's also not working out. But if I do a nice clean ln of x, that means I'll have u to the fourth in the bottom, which is clean. I do have this extra x, but anticipating what's going to happen when you do your du here, you're doing the derivative of ln of x. That is just 1 over x. That's going to account for that extra 1 over x there. So when you see powers of ln and you got this extra x on the bottom in the denominator, that's perfect because our du is going to have 1 over x dx. That's our du right there. And so that 1 over x dx is going to account for those two pieces. Perfect. And then that'll just be a power of u. This is what's going to work. Okay, so I'm not going to rewrite it, but if you know, think about it, that 1 over, the 1 over ln of to the fourth was going to be 1 over u to the fourth, since my ln is now u. That x on the bottom, 1 over x, and that dx together is just my du, and that's what the integral is when I substitute in terms of u. How do I do this? I got to rewrite that, or think about it as a negative exponent and do the power rule. Add 1 to that is going to be negative 3. Divide by that negative 3. Tack on your constant integration. And I can clean it up now or later. That's going to be u cubed on the bottom with the 3 and a negative out front. That's my antiderivative of this expression. My original has x, so I'm just going to go back to u is equal to ln of x. that's it. Okay, so keep in mind what you're trying to do to get this work out and solving the puzzle is anticipating whatever you set u to be, what your du is going to account for. And so when you do u is equal to ln, your du has that 1 over x and the dx. So you want that 1 over x in there for it to work out cleanly. All right. Okay. Let's see. Okay. I'm using that x squared plus 3 factor a lot. Just so you can see how you would deal with that in where it's in different situations, but it could be any other quadratic. All right. Not much choice. I mean, you don't want to do x because again, that doesn't get you anywhere. 8x is not going to be helpful because it's equivalent to doing it with x with just a multiple coming out of it. So for sure, x squared plus 3 again. I mean, let me go through another wrong one. If you try to use it with x squared, you do get that x that you need up top, but then you'll have a u plus 3 on the bottom, and that's not going to be helpful because we did another stuff up there. So, I mean, you'd have to do another substitution on that. And anytime you do something where you do 2 substitutions, it means you could have done it in one. Anyway, using x squared plus 3, this one I just want to mention because it's going to come out to one of the exponential logarithm sort of thing. All right, let's see how this works out. I do get that x dx, so that's going to account for that x there. Let me just divide that 2 out, and then that'll somehow combine with that 8 later, but I won't worry about splitting that 8 into a 2 and a 4 to get that 2 there. I'll just worry about that later. I want to get the x dx. The variables are important to get correct. The constants will just come together at the end anyway. All right, what have I got? Let me pull out that 8. I guess I could do this with, nah, I'm gonna rewrite it. I probably write extra steps than I would do if I was just doing it for myself. But I'm gonna pull out that 8. X squared plus 3 is my u. The x dx together is 1/2 the u. And so when I split it up, I'm going to pull that 1/2 out. It's going to become a 4 constant. And then I'll have du over u, which again I like to write as a separate integram from the du, but again they will write du over u, and it's the same thing. All right, what am I doing here? Antiderivative of, okay, so it's u to the negative 1. That is the 1 power that you cannot apply the power rule to. That is that one. So this is going to come up where it's just 1 over u is going to be ln of u. And I'll put in absolute values. So it's going to be 4 comes out to the front, ln of u plus c. Substitute back u is equal to x squared plus 3. And just be aware that, again, I'm not emphasizing the absolute value part, but a lot of times, since they know that x squared plus 3 is always positive anyway, they will oftentimes just drop the absolute value. So it's a little bit weird. They'll have it sometimes they won't. Sometimes they'll just note the fact that it's always positive anywhere, so the absolute value symbols are unnecessary. But either way is good. I just want to make sure you can recognize that it's going to become ln, and make sure you rewrite your answer back in terms of x. So that one or that one is fine. Okay, so natural logarithms comes up, and it's usually when you have a polynomial on the bottom, for now at least. All right, I got one last example, and then I'll do more examples in the quiz. I'm going to make this quiz have a few more examples of the same thing. You're just grinding it on, getting more practice. But mainly I need you to get practice. So I think I've assigned mostly odds, so you can check them in the back. All right, this last one is tricky a lot of times. I see calc students see it once in the notes for the professors, but then they forget it because it's such a weird thing that happens. They get used to grinding this out, and they get really good at this with the practice. This one's going to be unusual. It's going to have have a weird thing happen. Alright, that we can handle, but then you gotta remember how to handle it. And I'll put one like this in the quiz as well. I got a thing on the bottom. So usually like that, you really can't do an antiderivative of any kind of polynomial on the bottom. So it is a good hint that maybe you want to just make u to be the bottom, and it'll be similar to that where I'll get 1 over u. Well, I don't know if I'll get 1 over u. We'll see what happens. I'll definitely get u on the bottom. My du is just going to be dx, a 1 dx. So that's going to come out very clean. I do not have this x on top though, so this is going to be an issue. As of now, let's talk about what I have. I set my denominator to be u, so I'm going to have u on the bottom. My dx just comes out to a du straight out, no constants, no extra x or anything like that. But now I have x plus 3 up top that is not accounted for by any of these expressions involving u. So I'm writing in blue because I'm going to erase it, because I will have to convert everything to u. You can't do a half-done integral where some of it's u, some of it's x. That's not a thing you can do. So I've got to express this x plus 3 in terms of u. Now this is the first time I've done it this is the first time I'm doing it where I should actually take that expression, and as long as it's relatively simple, as in linear, I can solve it for x. I can get that x in terms of u by literally adding 2 to both sides. So u is equal to x minus 2 means I can rewrite x as u plus 2. And that's what I can use here. I can't do it for something like this because I'd have to take a square root and it's going to get messier. And I didn't need to there. But here I do need to. I have this issue of this extra x. And I need to use the fact that it's u plus 2. I'm going to write it in blue anyway. So that's equal to x. I also have that plus 3 there. So that's what I'm doing. I'm using this to substitute that x on top. And I end up with u plus 5 over u. Now, initially that looks like it maybe didn't really do that much because I still have a linear factor on top and bottom, but it is much better because the x minus 2 here, I can't split it up like I would do here. This is something we did in the last section where if you have a polynomial up top and just a single power of u, a monomial, a single term on the bottom, you can split it up. I could not do it here because it's x minus 2 on the bottom, but I can do it here. Oh, can you hear my microwave? My lunch is done. I'm going to go stop the beeper. Alright, I'm going to finish this up and then I'll eat. Alright, so I'm splitting it up. That's the advantage of getting the denominator down to a single u rather than a factor with multiple terms. I can reduce that. I can do whatever I want of that, but one thing to note is it is going to be, I erased it. It is going to be the logarithm. It's going to be 1 over u du. So that's the antiderivative of that is a logarithm. Let me see if I can cram it up here. I'm now ready to take my antiderivatives. Two separate terms I got to deal with. Antiderivative of 1 is just u. Keep in mind, I'm integrating with respect to u, this integral, so it's not x, it's u. I'm going to bring that 5 down, and then note that the antiderivative of 1 over u is ln of u, plus my c, and that's my antiderivative of this integral after I've broken it down. Last step, as before, rewrite everything in terms of x. I have u in multiple places. Each one is equal to x minus 2. So I have x minus, I'm going to fit this here. Can you see that? Okay. So this u is x minus 2. Then I have plus 5 ln of x minus 2 plus c. Now, we're good. That is an antiderivative. C is your arbitrary constant of integration. I will note that a thing that they do that comes up is, I'm rearranging it. So we're good. We took care of the antiderivative. This is an antiderivative, but I do want to note this comes up in later sections or next semester or in higher math classes. C, recall, is an arbitrary constant. That could be 7, it could be 13, it could be any number. When you combine it with this minus 2, because the minus 2 is a constant, this whole thing together is an arbitrary constant. So they'll absorb the c, or that negative 2 into the c, and they'll write their answer as x plus 5 ln of x minus 2 plus, and then they're going to use a different c, like a c2. So they're going to say that c2 is an arbitrary constant that's made up of just this constant minus 2. They don't write c2, they just write plus c. And initially it looks like, hey, what happened to that negative 2? But it gets absorbed in. This is a different constant that they're getting by combining that. So that's the idea. Any constants that come out of your process can be absorbed into your arbitrary constant, but the variables have to be left as is. So the answer in the back or on Chegg or whatever you use will show up like this. They won't have a separate negative 2. They'll absorb that into the arbitrary constant. Be aware of that, and also be aware of this thing, because it's going to come up once or twice, but seldom enough where people sometimes forget about the fact that you can actually manipulate that expression to get x sometimes, and then use it to replace any extra x's that are messing you up. Okay, that's it for that. You just got to grind out some practice problems, and then if you're still stuck, text me anytime you are stuck, and I can just say, hey, why didn't you try u is equal to this, or something. So by all means text me, but if you want to see more examples, just look at the quiz that I'm going to be doing for 5.2. I'll make sure I have a bunch of examples going through all these things that came up with these examples.